thanks very much for that introduction and for inviting me here, and hope you all enjoyed the film. And yeah, I figured I would give you some insights on some of the science behind sort of what goes on, but I'm not here to be sort of the stern finger-wagging skeptic about all the technical problems and whatnot, because this is not a BBC Nature documentary navigated by, David Attenborough or anything like that. We're not talking about that sort of movie. In fact, the thing that immediately comes to mind when I watch this movie is actually this one. So much so that I was actually genuinely shocked that there is no overlap in terms of like producers or directors or anything, or screenwriters, so far as I can tell. But yeah, it is not a nature documentary. It is a fun movie, and I certainly heard a fair bit of laughter and fun from it, so it certainly seems to have done its job. And so, of course, there are going to be inaccuracies, things that aren't quite the way they are in reality. Notably, for instance, the effect of the snake bite, which looks in the movie more like what you see in Raiders of the Lost Ark when they open the Ark of the Covenant, but in reality is considerably more pale. There are a handful of species that might cause you to pass out shortly after the bite, but most of the time, we're talking hours, sometimes days. The herpetologist in the film was absolutely correct that there are species out there for which, a good night's rest is sufficient. Even the strongest ones, very few of them are capable of the sort of turning you into something that looks like it's out of Resident Evil in the space of a few hours flight from Hawaii to LA. But it's a movie, it's dramatic. If you actually had what it looked like in real life, no one would watch it because it would all just be boring and everyone would get off the plane and get their anti-venom and nothing would happen. So, yeah, it's fiction. And, of course, the actions of the snakes, the movie itself lampshades this, and it's actually something that I really like about this movie, is that it's very easy to make various, I don't want to say monster movies, but scary animal movies with some sort of big shark or snake or something like that that is for some inexplicable reason just a homicidal maniac. This animal is the animal reincarnation of Hannibal Lecter, perhaps, or something like that, like the shark in Jaws. And people can take the wrong impression for that. In the aftermath of the original Jaws films, there was a wholesale slaughter of sharks, and people were terrified of these animals. And it took decades of Discovery Channel Shark Week series to actually sort of redeem their reputation. So one of the things that I do like about this movie is that it creates this entirely fictional pheromone to give it this sort of basis of these animals aren't normally like this. They're being affected by whatever, plot device they happen to invent, a pheromone or whatever. Not that it actually exists, but it's quite nice that they actually took the effort to say, no, they're not like this. And in fact, that is quite true. There's an old saying in herpetology by one of the big names about a century ago that snakes are cowards first, bluffers second, and fighters last. So if you encounter them, they will either stay hidden if they're already hidden, because they probably are, or try to escape. Only if they're cornered will they bluff and threaten and hiss and make elaborate displays, the cobra's hood, what have you, and only after that will they actually fight. And they acknowledge that directly in the movie, which I thought was actually quite great. And these animals are, like I said, very, very placid. A friend of mine actually, when this movie first came out, she was working as a venomous snake keeper at a serpentarium in the southern US, and to sort of help dispel any bad blood or whatnot from this movie, she actually would go into the king cobra cage at the serpentarium and just sit there reading a book with I think he was about 12 foot long at the time, king cobra just sitting there next to her. And he never did anything, because in reality, that's what they do. They hide. But of course, again, that doesn't make for a very good movie. But I do want to actually single out one of the things that I found really great about this movie, which is the ability of the snakes to basically get everywhere in the plane, which is actually not only accurate, but is actually one of the key things about snakes. So this is the scene where they can't even barricade them away without having to use chemical fire extinguishers. And this is central to the movie, along with the fact that they are venomous, except for that enormous python. Basically, if this were the same exact plot, but the villain had used a tiger or some wolves or something, it would not be a particularly interesting movie. It would be like, oh, there's a tiger in the cargo hold. Okay, lock the doors and call animal control. We'll deal with it when we get to LA. Whoop-de-doo, done, end of film. You know, it's just an animal in a cargo hold. The fact that the snakes get out, and they made a mention of leaving a door open, but the animals get everywhere, and that's actually a crucial part not just of the movie, but of snakes themselves and what makes them snakes and why they evolved to become snakes. So snakes are one of the most wildly successful group of organisms, and not just they themselves, but there are numerous groups of organisms that have independently evolved the long, skinny body form of snakes. There's numerous types of legless lizards, of which snakes are simply the most successful. They are a type of lizard. And a big part of this is their ability to move through highly complex terrain and get into all these little crevices to deal with environments that nothing else can, and to actually benefit from those environments. So as should come as no surprise, compared to a limbed animal of similar mass, snakes can go through much smaller holes, wedge themselves into much tinier crevices, simply because they are long and thin. A 2-kilogram snake can fit through a much smaller space than a 2-kilogram dog or a 2-kilogram rabbit or what have you. And so this is fantastic for infiltrating planes, but also for going down rodent burrows to try to find delicious little rodents to eat, or into crevices of rocks to avoid predators. But it's not just fitting into the small spaces. They are, as I like to say, the masters of cluttered, complex, and intricate environments. So the more cluttered, the more obstacle-ridden, and the more difficult to deal with, the better they do. Whereas everything else, everything with limbs and all of our devices with wheels, get worse. They're masters at moving through highly irregular terrain, such as rock fields. It doesn't show up quite as well, but grass is an excellent environment for snakes. The saying snake in the grass is not just a figure of speech, actually. So snakes in North America were actually not a terribly big component of the ecosystem until about 11 million years ago, when the climate cooled, grasslands expanded, and you see in the fossil record basically instantly the number of snake species skyrockets, and they diversify explosively because this dense grassland is fantastic for them to move through. They also do extremely well in deserts. You go out to the desert southwest in the US, there are snakes everywhere. And it's because sand is a very difficult environment for a lot of organisms to move in, mud as well. I'm sure some of us have gotten cars stuck in mud, things like that. It's hard to move in, but they move across it extremely well and extremely effectively, sometimes even in unique ways, which we'll see in a second. They can even climb highly effectively. You saw them coming out through the mask system in the airplane, but that's not that unusual. Many, many species are arboreal, will drape themselves gracefully across tree branches. Or even this is actually one of my favorites because this picture is not rotated. This is a snake just going straight up a tree. No problems, just using the bark and just straight up. And this is a huge part of why snakes are snakes and why they have been so incredibly successful as a group. They are incredibly diverse, live on basically every continent and island except Antarctica and a few very isolated cold places. And it's because of their ability to succeed and have such an amazing movement through the very environments that everything else has trouble with. And a large part of that is how they move. And so when we move, we typically walk or run. If you're a four-legged animal, you gallop. And the transition between these is largely governed by speed. You walk until you need to go faster, then you run, and if you have four legs, you gallop. And you can modify it in response to the environment a little bit, but most of it is governed by speed. In snakes, they have over 20 different modes of locomotion, which can broadly be grouped into four major classes here, all of which are keyed not for speed, although they do differ in speed, but it's mostly in response to the environment. You give them a particular environment and they will automatically pick that particular form of locomotion. So at the top you see rectilinear. This is one of the oddest ones. This animal is a large boa constrictor. It's moving, it's a little cut off there. This is sped up fourfold, this weird belly rippling movement. And this is entirely powered by the skin. If you were to take an X-ray, you would just see vertebrae and ribs gliding forward smoothly. The ribs aren't moving. This is just bits of skin being picked up, moved forward, put down, pulled backwards in these ripples. And as a result, they can move through holes that are as big as their body diameter, and in fact, they can usually move through holes that are smaller than their body diameter by collapsing their ribs at that particular point. So they can move through almost anything, even smaller than their bodies. But, as I mentioned, it is fourfold sped up. This is actually very, very, very slow. Here, this is something called concertina locomotion, after the instrument, the accordion-like instrument. And it's sort of an inchworming style locomotion, if you sort of think of it that way. The snake reaches forwards, and then it anchors itself by bracing against the tunnel walls, pulls its body forwards, and then repeats, just like an inchworm, sort of scooting its way along a branch. And they can do this inside of a tunnel, they can do it on a flat surface, they can do it on a tree branch. This allows them to move through these featureless environments, and especially in tunnels, highly effectively. But it lets them be a little bit faster than this. This is probably the most emblematic of snake modes of locomotion, slithering. So when you think of snakes, you think of slithering. It's even in the Harry Potter house name. So this is what everyone thinks of, these sort of undulating wave. They send these ripples down their body. And this is what most snakes will try to do if they can. If you put them in an environment, they will try to do this movement. And it's one of their absolute fastest. It is tremendously capable, and it lets them move through a huge range of environments. And finally, this bizarre form of locomotion called sidewinding that's seen mostly in desert vipers. Only a few species are capable of doing this. Certainly not all of them, and there's some really cool work being done on this, but it's this strange sideways mode that we'll talk about a bit later. But slithering, I think, actually goes back to the primary point of how these animals interact with complex environments. Because as you watch, you can see the animal bending its way through this environment, and you can see it touching all these various rocks and crevices in the rocks. What it's doing is it's sending these ripples down the body. They're hitting things in the environment, rocks. If this were grass, it'd be the grass tuffets, things like that. It pushes against those, equal and opposite reactions. The snake goes forward. And I like to describe this almost like horizontal rock climbing. When you're trying to climb a rock wall, you find these handholds and you're fighting against gravity, and then you pull on the handhold and you sort of pull yourself forwards or upwards in the case of rock climbing. So in this case, the snake isn't fighting gravity, although they can slither upwards vertically. It's fighting friction, but the same principle applies. And has anyone here done rock climbing? A few folks. Okay. What's the easiest thing to go up? Something with lots of handholds or very few? Lots. You know, if you have almost no handholds, if you have something that's almost sheer glass, you're not getting up. If you have tons of handholds, at a certain point it just becomes like climbing a ladder. Same thing is true for snakes. So as they're moving through this environment, they're trying to find spots to push off of against the world. And the more obstacles, the more spots they have to push off of, the more handholds, the better they can do, the more choosy they can be, and the faster they can move. And in fact, in studies with these animals, you can see as you have more and more clutter, more and more environments for them to move through, they actually get faster and faster and faster until you reach some limit where they're just so confined they have difficulty moving. But they are extremely good at moving through these sort of cluttered environments. Where everything else gets slower, they get faster. So if you move through more and more cluttered environments, you slow down. Same thing for any limbed animal, wheeled robot, whatever. You either have to pick and choose your footholds, or if you're not, you just slip and fall a lot, and that still slows you down. They get faster, and they can't fall. They're snakes. So this makes them really potentially useful for a robotic replication, which is part of what I do. So if I want to go into cluttered, complex, and confined environments, a snake robot would be ideal because that is what snakes evolved for moving in these cluttered, complex environments and getting into narrow spaces. So for instance, this is a building that collapsed after an earthquake in Kathmandu, and this particular building, I mean, if you tried to get through this with a wheeled or legged robot, it's going to have some serious problems. It can't fit through a lot. The terrain is highly irregular. But for a snake, those irregularities not only aren't a problem, they're a benefit. They're something that allows it to move faster, go slithering through something like this, find survivors, figure out where they are, things like that. Where do you dig? That would be an excellent use. Or if I have some huge, complicated machine that I don't want to fully take apart, I want to go poke around inside and find where the flaws are, a snake would be an excellent choice. So here you see, most of what you see is a truck engine. Some of you who are familiar with engines might be like, I don't recognize this particular tube thing in there, which is because it's a diamond python. This is from Australia. Somebody parked their truck, and the engine was still warm, and so this diamond python decided to crawl inside of the truck to stay warm at night. Despite the name, oh, it's cut it off, it's Jamie Irwin. It's not actually a relationship to Steve Irwin or any of his kids. It's just a common name in Australia. But yeah, the animal just manages to easily slip through this highly complex environment and can get into spaces that otherwise wouldn't, as well as moving beyond the world. So this is Murray boots on Mars, but you'd see similar environments out in Utah. And if I want to go send something to go poke around up here, maybe poke around under the rocks for little green men, a rover is going to be a real problem. Even that new helicopter they have on Mars, that might land on top, but it's going to have a real problem trying to land on these sort of sand and debris-strewn rocks. But if you can find environments just like this out in Utah, Nevada, that sort of area, which is why NASA does testing out there, and under half of these rocks in a similar environment in Utah, there'll be snakes hiding under the rocks, waiting to eat something that comes by. Because this is what they do, and what they do so well. And so in order to do so, it's not enough to make a snake robot. It's not enough to just string a bunch of motors together. That's easy. You have to manage to figure out how to convert these movement modes, these strange and bizarre forms of limbless motion, into something the robot can do, taking into account that, the robots aren't as good as the real snakes. The robot might have a dozen, 2 dozen, maybe 3 or 4 dozen joints compared to literally hundreds of vertebrae in a snake. So it's not going to be as flexible, it's not going to have a brain, a sensory system, so on and so forth. So how do we copy this? How do we get a snake robot that can do what snakes do? And oddly enough, some of our best research has actually been on one of the weirdest forms of locomotion, which is sidewinding. This bizarre sideways form of locomotion I mentioned earlier. It's seen in a handful of desert vipers, and it's an odd behavior to look at. There was actually, you briefly see one a couple of times doing what's actually passably good sidewinding for a CGI snake in the movie. But it's very confusing to look at, And there's a saying in herpetology that if you spend enough time looking at sidewinders, you'll go mad. I spent my entire 3-year postdoc working with them, so take from that what you will. But it turns out that if you stare at it long enough, it's actually not that confusing. Watch the head as it moves. You know? You see it picks the head up, moves it forward, puts it down. Picks it up, moves it forward, puts it down. And then the same thing happens to a point on the body immediately after the head. Picks it up, moves it forward, puts it down, just a little bit later. So you have this sort of lagging system where every point on the body is picked up, moved forwards without touching the sand, put down, and then it stays in static contact. And so it's almost like walking. It's sort of like what we're doing with our feet. We're picking it up, moving it forward, putting it down. This snake has basically relearned how to walk. And it does so in order to avoid disrupting the sand. It turns out you can also model this quite easily by just a series of bends from left to right on the body, along with a series of up and down movements. So it leaves these weird diagonal tracks, and it's extremely effective at moving across sand. Level sand, but also inclines. One of the earliest studies I was involved in was because a group with a snake robot took it to explore some caves in Egypt that they thought might have mummies in and whatnot, and their robot couldn't get up a modest sand slope. So we studied how real snakes move on sand slopes, and we're actually able to replicate this behavior in the robot and get it to go up sand. Admittedly, not quite as well as a real snake, because it's a robot. They're not that good yet. But we were actually able to move it and achieve the similar sort of motion, because it turns out that what snakes are doing is fairly simple. As sand gets steeper, it's easier for it to avalanche downwards. We've all experienced this. And so if we're climbing a sand pile, we tend to stick our feet in deeper to get that higher reaction force. We stick our feet really deep into the sand. What they do is essentially they use these static contact regions here, the sort of regions where the whole body is in contact, and they just make them bigger. So it's like having deployable snowshoes. It's like if you went out in the snow and your feet just got bigger so that you wouldn't sink into the snow without having any problems. And so as a result, these animals can go up any slope the sand can form, and we got pretty close to that. This is from 10 degrees, but we got up to 20 with the robot before it started failing. We also managed to copy how they move. They can move in these big arcing turns, or even they do this sudden, almost instant on-a-point turn, which is actually, if you think about it, quite impressive when you're on sand. If you're on sand and you're running and you suddenly have to turn, you've got to stop yourself and generate a lot of force, and it's real easy to slip and have your foot come out from under you. But here, he's moving, and then you see my shadow, and I scare him, and off he goes in a whole new direction, no slip, no problem. And with my collaborators at Carnegie Mellon, we were able to implement this in a robot and actually get it to have some level of control. So we're sort of slowly making our way, but this is sidewinding. This is a very bizarre desert sort of form of locomotion. You can see the robot has a pretty wide path. It actually suffers when obstacles are placed in its way, just like we would. So most snake robots aren't going to typically use this unless they're doing something that you don't really need a snake robot for. Concertina is another, as I mentioned, this sort of inchworming mode that we've recently managed to start by feeling for the tunnel walls. So what's happening here is both of these robots are actually executing the same code, but what they're doing is they're feeling for the tunnel walls. They're feeling for when they've got a good bracing anchor, and then they're adjusting their wave afterwards. So both of these are governed by exactly the same code, just like the snakes seem to be just feeling for the sides of the tunnel in order to move. But of course, slithering is the ultimate mode of snake locomotion, the one that they're most recognized for, the most versatile, and the one that's most effective at moving through highly irregular terrain. Unfortunately, it's also one of the most difficult to replicate, because in order to do this effectively, you not only have to push off of all these handholds, but you have to make sure that your forces are all pointing in the right direction. And so that's proving to be quite challenging for robots. A group over in Japan that I've been in conversation with recently has a reasonably good snake robot, and this particular robot is really, it looks very sort of snake-like. Not perfectly, but for a robot, it's doing pretty well. And a key part of this is that it has basically, it doesn't know what's happening to its tail. The head is saying, I'm going to turn left and right, left and right. Everything that happens down then, the head tells the next segment of the body what to do, and it adjusts it based on what it feels, and then it passes it down to the next one, which then adjusts it again, and then passes it down and adjusts it again. And so it's sort of like a game of telephone. It's getting changed all the way down the line. So the head is the only part that actually knows what it's doing. By the time it gets to here, it's been so radically changed compared to what it was in the head that it's just totally different. This amazing decentralized control system that's also very computationally cheap. But it is still slow and jerky compared to the real snakes. So a lot of what I do is I try to bridge this gap by understanding the mechanics of how the snakes are actually moving. So here's a little bit from some of our recent research. So this was taken over at Neomed, actually, in a biplanar X-ray system. So this is X-ray high-speed video. It's slowed down about threefold. Here you have a side view. Here's our sort of top-down view. And you can see as the snake is slithering by, you can see all the vertebrae. You might be able to make out the ribs. They show up a little bit better on this one. But we're trying to understand how they're moving their bodies. And if you look carefully, you can see these tiny little black spots here, 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 and there's a few that are going to come into view here. So those are actually implants in the muscle that let us understand what their muscles are doing and how their muscles are changing length. So they're just inert metal beads. So they're completely harmless to the snake, but this lets us track their movements and help us understand how they're doing what they're doing, as well as starting to get a handle on some of the more unusual things, like watch the body shape when it bends. Those ribs are shifting side to side in this very unusual way. We have no idea what they're doing with that. One of probably the biggest thing, ask me 100 things about snake locomotion and snakes, and the answer for most of them is going to be, we don't know, and 90% of the time that's because we've never even looked. No one's even tried. No one's even examined this sort of stuff. So there's just so much that is left unknown. One of our recent discoveries was that they can actually use vertical movements just like they can use lateral movements. I seem to be having some video glitches with the top one. It'll sort itself out in a second. But generally speaking, they can, just like with slithering from side to side, which used to be primarily called lateral undulation, they can bend up and down and exert forces, and we were able to replicate this in a robot. And this actually seems to be what these animals are doing in reality. We've done some experiments. This is with my collaborators at Johns Hopkins University, with a snake moving through truly random terrain. The block heights are determined by a series of random numbers, and they use sort of a roughly equal proportion of vertical bends and lateral bends. So it seems as if slithering really is a fully three-dimensional behavior. If you confine them to 2 dimensions, it becomes 2-dimensional. But in reality, these animals are using all 3 dimensions of their environment to really leverage that. And so this is one of the exciting new directions. But generally speaking, it sort of showcases just how well these animals move across highly complex terrain. Aside from a brief bit of exploration here and there, this animal is just gliding through this highly irregular terrain. This would be the sort of thing that if you put a human of equal size or appropriately similar size into that, it'd be like something from, what was that, American Ninja Warrior or something like that. But it just glides through gracefully. And so we're hoping to sort of bring all of these together and really understand how these animals work and how they interact in order to use the real snakes to make better robots, but also we can use the robots to learn about the animals, test certain behaviors out. What happens if the snake doesn't do this particular behavior in this environment? Will it fail or just go slower? The robot does what I tell it to. The snake, not so much. But this has tremendous potential for a whole new generation of robots that are capable of moving through these highly complex, intricate terrains with grace and ease to get at things that we otherwise couldn't, as well as helping us understand our slithery friends. So with that, I'd like to thank the many folks who have helped me over the years, my funding sources, my collaborators, my students, and I have 2 snakes with me, a robotic one as well as a living one. So we'll start with the robotic one. But feel free to ask questions, etc. And once the living one comes out, you'll be able to come and see her, meet her, touch her, etc. She's an outreach animal. So here we go. This is not the sort of the full code version. This is just sort of a simple, goes through a simple sequence of demonstration code. There we go. Straight and sidewinding, except it's upside down. There we go. Sidewinding. So yeah, so using this, we just have a series of very simple commands. The robot goes through sidewinding. It's going to go through a few more cycles, then it's going to reverse itself. I think it's getting a little hung up on some aspects of the carpet. Popcorn bits, yeah. I'll be cleaning popcorn bits out of my servo motors next. No, it's good. These are pretty robust motors. You can hear a little clicking when it's getting hung up on things. But yeah, so this is that simple sidewinding mode, and in any second it's going to transition, here we go, to slithering. And actually this is sort of the opposite of what I was talking about. This thing is trying to slither and it's getting nowhere because it's got nothing to push against. It's got no sort of environment. If I give it something to push against, all of a sudden it moves. So similar for a real snake, if the environment is so featureless that they can't push against anything, it's like trying to do rock climbing on a glass wall. You just can't. There's nothing to hold on. You slip and slide around, or like putting a kid with no ice skates in the middle of an ice skating ring. They're just going to flail around, and maybe they can make progress in some direction or another, but ultimately it's just going to be a miserable failure. But give them structure, give them environment, give them something they can push off of, and they'll fly. So let it finish its slithering cycle, and then I'll grab Penny.
Can I ask you a question?
Yeah, go right ahead.
You mentioned that only certain snakes are capable of this.
Mm-hmm.
If you were to take a snake from an environment that didn't require this type of movement and just drop it into a sandy or some type of environment that did need it, would it just figure it out, or
Oh no, I wish I had included these videos hidden in the back. I should have. So actually one of the studies that I did early on was I was at Zoo Atlanta, had access to all their animals, and so basically it was like, let's throw everything from Zoo Atlanta in the sand pit and see who sidewinds. And it was actually quite interesting. Most species were able to slither on the sand extremely effectively, except for the vipers. For some reason, something is, I don't want to say wrong with vipers, but they struggle with sand. And the crazy thing is, they will just, about 25% of them literally just cannot move on sand. You put them in sand and they will thrash back and forth, getting progressively angrier until they stop and just start hissing at you and rattling if they have a rattle. Once you tilt it to about 5-10 degrees, it's universal failure except for the sidewinder. And this actually mirrors what we see out in the wild. If you go out to, Yuma, Arizona was my favorite field site. You go to the hardpan desert with lots of creosote bushes and things like that, and there's tons of snakes of all sorts, including tons of different rattlesnakes and vipers. But the moment you go to the smooth desert sand, the smooth sandy areas, you still have all the other species, all the colubrids, the sort of main group of snakes, coach whips, rat snakes, what have you. But all the vipers disappear the moment it becomes pure sand, except the sidewinder. It's the only one that can invade that habitat. And my collaborator, Dr. Jessica Tingle, she's a postdoctoral researcher currently working in my lab. She's the real expert on sidewinding, and she actually has this cool set of data about the differences between the sidewinding snakes from the Sahara, because the Sahara Desert is about 7 million years old, versus the snakes from the American Southwest, because the desert there is only a few 100,000 years old. So the snakes have had far less time to evolve and to become proficient sidewinders. And so there's some really cool stuff going on, but it seems as if, long story short, most snakes that cannot sidewind just can't. They can't learn to do it. It's you either have it or you don't. There's some really cool data that she has with some species that can sort of, some individuals can do it, some can't, even siblings between a clutch. So that's bizarre, yeah.
Especially interesting.
Yeah. Yep. Oh, yeah, I saw someone. Oh, no worries.
Sidewinding.
Yeah.
So do you think that if you had some way to motivate the snake, such as hot sand,
Yeah.
do you think, have you tried, that may affect the efficiency of sidewinding and non-sidewinding?
Maybe. So motivation is always the sort of X factor. How do you motivate these animals? And especially with snakes, because they're not like, a dog where I can have treats and I can give it a little treat. They eat once a week, once every 2 weeks, once every month. And so, where is she off to? Okay, she's behind me. So it becomes very hard to motivate them. So we can't ever say this animal cannot sidewind. What we can say is, well, we put it in the sand, it failed to move under these conditions, and it got very obviously aggravated at us and our presence when it did so. And so as a result, it's like, well, if it could sidewind, I would say surely it would have, but if it was that pissed off at us, then it probably would have if it could have. But it's all, it's like proving a negative. There are no white ravens. You can find a white raven and prove it false, but you can never prove that there isn't one that you just haven't found yet.
Is she snuggling with you?
Sort of. She's just climbing. So her species, so this is Penny. She's our official lab outreach snake. She is a Taiwanese beauty snake. And so she's actually basically the same thing as the black rat snakes around here, just from the other side of the world. Same sort of ecological niche. Around here, if you've got chickens, something's eating your eggs, it's a black rat snake. That's what you'll find inside your chicken coop. In Taiwan, you have chickens and something's eating your eggs, it's her. Same general sort of thing. Sort of jack of all trades, master of none, pretty good at climbing, but not super, super good. Not as good at climbing as a tree snake, not as good at swimming as a water snake, not as fast as a slitherer, as a racer. I like the phrase, a friend of mine has German Shepherds, and he says they're the second best dog at everything. And that's sort of these guys. They're not the best, but they're the second best at a lot of stuff. They're versatile. So right now she is basically just trying to get herself safe and secure. She wants a nice firm grip to sort of feel like she's supported. Yeah?
That actually brings me to another
Yeah.
question about the movie.
Yeah.
So, as far as I'm aware, snakes always like to be gripped around something.
Yes, yeah.
But most of the snakes, when the seal was broken, most of the snakes flew right at them.
Right.
Is that realistic, or would it be?
Yeah, hard to say. Generally speaking, their grip is actually quite strong. So like if I were to try to forcibly remove her from my arm right now, she would actually give me a run for my money. She's quite strong despite only being about 8 feet. But at the same time, the oxygen dropped. It got super, super cold. These animals are, as they're colloquially called, cold-blooded. So their body temperature does drop with the environment. But that said, if you're big enough, it takes a while. So 20% realistic, 80% plot device. Slash budget saving, we're sick of animating the snakes. Yeah.
Yeah, I think you said earlier that your research shows your robots aren't great at vertical mobility.
No, they can use vertical mobility to propel themselves forwards.
Can they do steps?
Yes. So my robots, yeah, I think I could probably manage to get them up steps if I matched the wavelength, yeah. Yeah, snakes themselves can also easily get up steps. Yeah, but yeah, it's a big part of the issue with some of the robots is just how many motors do we have? Because Penny has 200 and I want to say 225 body vertebrae. It's been a while. I'd have to look it up in my logs, plus another 100 in her tail. Whereas that Snakebot has 24 motors, 12 horizontal, 12 vertical. You just can't match that sort of dexterity. So, and then I could add more motors, but then money, and then power demands, and so on and so forth. So, but we're getting there bit by bit. I like to say snake robots now are where humanoid robots were 40 years ago. So, yep.
I have a dumb question.
No.
When do you tell when the body ends and the tail begins?
Ah.
Because isn't that just the tail of the head?
Yeah, excellent question. No, that is an excellent question. That is an excellent question. So what determines tail versus head? We think of it based on limbs, but actually one of the defining features of vertebrates as a whole, including things like fish, is what's called the post-anal tail, that we have some anus, some out hole, and there is a muscular extension beyond that. If you look at, for instance, bees or lobsters or earthworms, they don't have a post-anal tail. That the last segment of their body is where the anus is, essentially. Are you going to go into my hair and mess it up? Yes, probably are. But so the trick correspondingly with snakes is right here, actually. So this is her cloaca. It's the universal sort of out hole, reproduction, waste, and everything comes out through there. So everything anterior to it is body. Everything downstream of it, so to speak, is tail. Does she have a neck? That is the question. And what is a neck? Because on one hand, her muscles from her head to her, so most of her body muscles are just the same thing over and over and over and over again. Just literally one after the other, one after the other, one after the other. But there's a special sort of anatomy around after her head because there's an end to the snake. You can't have the muscle span forever. But on a developmental time point, if you look at us, certain genes get turned on in our head, our neck, our shoulders, torso, lower back, hips, tail if we had one. They don't have any of the neck genes. It goes skull, body genes. So anatomy tells us one thing, development tells us another. What's true? What's not? How do you define neck? Do you prefer anatomy or do you prefer development? Is it genes that make a neck or is it anatomy that makes a neck? So it's actually a pretty intricate and interesting question. Yeah?
You were talking about the number of vertebrae it has.
Yeah.
Is that a pretty consistent number between snakes, or is there snakes that...
It's not even...
Even when you go larger or bigger, that like, is there a minimum snake size, essentially?
So I'll sort of work through it. First of all, it's super variable even within clutch mates. I can hatch a clutch of eggs or have a bunch of live-born snakes that are full siblings, and they will have different numbers of body vertebrae. Sometimes, usually it's about plus or minus 5%. So if she's got 200 vertebrae, that would be about plus or minus 10 on each side. And similarly, the tail. So even full siblings will have different numbers. There's different numbers between different populations of the same species. Different species can have wildly different numbers. So some species, it will be as short as, I believe the shortest I'm aware of is 110 body vertebrae. The longest I'm aware of is close to 400. And it generally follows length. Shorter snakes, on average, have fewer than longer snakes. But that it's sort of like on average. There are short snakes that have a lot, there's long snakes that have few, but sort of mile high, sort of zoomed out view. Bigger means more vertebrae. Yeah.
We have to wrap up.
Oh yeah, yeah.
Stick around.
I am absolutely going to stick around, and you can come up and meet Penny. So she is very friendly. She is an outreach snake. Like literally the entire reason I have Penny is because I can't use my lab animals for outreach, and I got sick of bringing my personal pets. So she is just an animal who she lives in my lab, and she has done outreach everything from adults down to third graders. And so she's very tame, very sweet, never bitten anybody. You can come over and say hi.
I'm going to have you hang out in our office
Absolutely.
for a second, because we have a sold-out showing.
Oh, so we have a next show? Okay. We could do snakes in a theater.